Sorry, can you say that again?
What is the happy government?
Semesters when things were messed up for reasons other than ice. All right. Homework 4 isn't due today. I hope that you saw my email that that deadline has been pushed to Wednesday. Because of the snow day that we had on Friday, I recorded that little 15-minute homework help just because I knew that between the end of today's class and Wednesday maybe would be a tight turnaround. So hopefully you were able to use the information from that little help video on Friday to get you down the road a little bit on homework 4, and then I'll show you a few more things today that hopefully help get things across the goal line. So before class on Wednesday, I've just handed out the revised schedule, and that's posted also on Blackboard. One thing that I changed on there that is like unrelated to this particular assignment is the assignments that are due before exams, I made it due the day before the exam, like around class time, so that then I can post the solution and you have a day to look at the solution before you have the exam. And so that's just an effort to get you some exposure to the right answers in case you had any uncertainties, and to clarify the topics in your mind before we have the test. Any questions related to announcements or schedule related things? All right, well, we're going to continue talking about precipitation today. And do you remember what are the three main forces that cause precipitation that we've talked about before? All three of them cause precipitation through lifting. And so what are those factors that lift air? Temperature. What was the specific technical terms for instance, what's the name of the one where there's a mountain in the way and the air has to go over the mountain? I wish we were having a quiz today. That'd just be so juicy to stump you. Orography. Austin's got it. It was a group quiz. You're 1 for 1. All right, what about when it's the afternoon thunderstorm? Like when the sun is shining down during the summer, it heats the air at the ground. What's that? Convective lifting. All right, good. And then the third that we talked about was when a mass of cold air comes together with a mass of warm air. That's convergence, frontal lifting. Good. All right, so those are the three factors that we talked about before that sets off that chain reaction of warm, moist air rising through the atmosphere, expanding because of the decrease in pressure. As air expands, it cools, and then cool air can't hold as much moisture as warm air, so that excess moisture has to begin to condense on particles, and the droplets form in the particles until they are bouncing together and aggregating, and they get too heavy and they fall down through the air. So that's the chain reaction. Now, the biggest storms that cause the most spectacular flooding aren't related to orography, frontal lifting, or convective lifting. The most significant storms are usually related to hurricanes. And at least here in the Midwest, we can be under the influence of storms that come out from the sea. And so I just wanted to point out that the design storms that are used for sizing things like dams, and I've talked about this before, don't use the same kind of statistical extrapolations that are just based on like the afternoon thunderstorm model. And the afternoon thunderstorm is probably going to be the factor that predominates like a 10-year storm or a 25-year storm. But then when you talk about a storm so big that it has a return frequency of 500 years or longer, it's going to be one that has, let's say, moisture from a tropical storm coming together at the same time as a cold front from the north. So we'll talk more about that, but I wanted to mention that orography, frontal lifting, and convective lifting isn't the final word on those things that cause precipitation. So on the subject of tropical storms, I did this screen grab a couple of years ago, back when there was a storm that was coming ashore in the Carolinas, and just the amounts were really striking. If you remember that like a 5 inches in a day would be, wow, really a lot of storm. You know, we had a really rainy, was it Friday? It was pretty rainy, or was it Thursday, where it just rained all day long? It was Friday, right? Yeah. It rained all day long on Friday, the day that school was canceled. It didn't end up actually even getting cold until later in the day, if I remember correctly. But I looked it up, and we got about 2.5 inches of rain out of that storm, and it seemed like a lot. It was raining all day long. You know, the creeks were flooded, and that was 2.5 inches. Now look at this, 35 inches of rain along the coast. I mean, it's almost hard to comprehend more than 10 times as much precipitation in a 24-hour period. But that's kind of the rainfall that you can get from these tropical storms. It's really significant. All right. We've talked about intensity, duration, frequency curves on several previous occasions, and they are what we can use when we're trying to do something like the rational method, where we have to know not only the intensity of a storm, but also the duration. And what we ordinarily do in the rational method is we set the duration of the storm equal to the time of concentration for the contributing area. And the reason for that is the worst case scenario. That's going to give us the largest peak rainfall. Because if the storm duration is less than the time of concentration, then only a portion of the area would be contributing to flow. But if the storm duration is longer than the time of concentration, then the intensity would be lower. So it's the match of those two things. It's when the storm duration equals the time of concentration for the watershed that you'll see the largest peak runoff. And so that's kind of a little bit about how we select the duration for the storms. It's not that, you know, a parking lot that has a time of concentration of 15 minutes is only going to see storms that last for 15 minutes. Of course, that parking lot will also experience a short 5-minute storm. It would experience a long storm that lasts for 2 hours, but the critical duration is the one that matches its time of concentration. That's what will yield the largest peak runoff. So the scale on the vertical and the horizontal axis here is logged to give it that curved shape, and the advantage of having it logged is that then it kind of compresses and spreads out the data so that you could show a 24-hour duration on the same figure that you could have a 5-minute duration storm. You know, if it was a linear scale, it would have to be such a long figure to have both the 5-minute, the 10-minute, the 15-minute duration, but then also going all the way to 24-hour. So that's why we've made it log on the horizontal axis. On the vertical axis, it's not going over as wide a range, but it still allows you to kind of see more of the data than otherwise would be possible. I think we've talked about all of these terms, so we'll skip through certain things kind of quickly. Hydro 35 is what the precipitation frequency data server is looking at. That will come to that website in a moment, and maybe you already have looked at it, but there are these analyses that NOAA has done to look at how rainfall patterns vary geographically. And you can see that this is the 2-year, 60-minute precipitation storm, and this is the depth, not an intensity. This is the depth, but you know, as you might expect, coastal areas like in Miami are going to have a much higher rainfall depth than in the plains regions, where they don't have as much warm moisture coming off of the ocean to fuel that. But with like a 2-year 60-minute and a 100-year 60-minute, we could extrapolate and interpolate in between and find the 60-minute duration storm for other return periods besides just the 2 and the 100-year. And so this is one of those slides that I introduced in that brief 15-minute video and explained how you can interpolate both the storm duration and also the storm's return period. So if you have just the 5, 15, and 60-minute storm depth, then you could find the 10 and the 30 with the factors that are listed there. And then if you only have the 2-year and the 100-year storm depth, then you could find the 5, 10, 25, and 50 by using the coefficients in this empirical equation. And so, you know, these, like the typical gap between the 2-year and the 5-year storm, there's a pretty consistent relationship, even though there's much different precipitation patterns across the United States in terms of the amount. It's pretty typical that for instance, the 5-year storm would be 20% larger than the 2-year storm. And so they just use that pattern of extrapolation regardless of your location. So these equations are location independent. Now, they break the United States up into zones, and these figures are expressing the rainfall amount relative to time. So at the beginning of the storm, at time 0, none of the precipitation has fallen yet. And at the end of 24 hours, you can see it's up to 1.0. That means effectively 100% of the precipitation that falls during a 24-hour storm has happened by the end of the 24 hours. But if you compare like coastal Washington, which is type 1A, type 1A never gets quite as steep, or at least not for as long, as a type 2 storm. A type 1A storm pattern is that the rain starts and it does go through a period of elevated intensity, but think about what this curve would look like if it was just the same rainfall intensity all day long. If the intensity didn't vary at all, it would just be a horizontal line. And so the type 1A, I think, is probably the closest to that horizontal line, which means a smaller amount of the storm happens in a big burst, compared to type 2 storms where only maybe about 20% of the storm happens through the first 10 hours, and then well over half of the storm happens in the period of maybe just a single hour. And then the remaining 20% of the storm occurs in the last 12 hours of the storm. So, you know, the different regions, whether it's the Gulf Coast or the Midwest or, you know, the southern Pacific coasts, there's these different observed distributions, and our table has this, our textbook has this table where you could multiply the known depth by a fraction, and then you'd know how much precipitation has fallen up to a certain amount of time in the storm. So that's one of your homework problems, actually 2 of them, because I ask you to use the 24-hour storm for one of the problems, and so that's multiplying this type 2 column by the precipitation depth and graph it versus time. And then another one of the problems is looking at the 6-hour storm distribution. And so again, you have time versus the precipitation amount at a certain fraction of, as a fraction of the total storm amount. Any questions about temporal distribution? Not every storm follows this pattern, of course. You know, this would suggest that maybe you'd be forgiven for thinking that every storm has this period of maximum intensity 10 hours in, and that's not true. In a certain 24-hour storm, it could be that today's storm has that maximum intensity period after just 3 hours, and then it tapers slowly for a long time. These are just maybe the median, like it's an average of all the observed storm behavior over a long period of time. And so it's kind of, if you don't have any specific historical precipitation data, if you're just measuring the precipitation amount on a daily basis, but you need intensity to perform an analysis of how a certain watershed is going to do, there needs to be some way to translate, like a model, to translate depth into intensity. And so this is just one way for us to take a precipitation depth and translate it into the intensity. And we'll use this a lot when we're doing the computerized modeling of watersheds using WMS. We'll use this type 2 24-hour distribution. All right. There's a couple of websites that are pretty informative and illustrate different aspects of precipitation. And the PRISM website that's made by Oregon State, I think is useful because it has some really nice figures that illustrates the average annual precipitation. And this is where you can get an idea of how much rainfall in a year is typical for a certain region. And so if you look here in West Virginia, most of it's this kind of aqua color, which is in the 36 to 40, oh maybe that's green, maybe we're in the 40 to 50 range with this color. And then in the mountains is where it switches over to blue, which is in the 50 to 60, and it looks like there are a couple of locations in the high mountains where it even gets into the 60 to 70 inches of rain per year. Of course, out in the western United States, which is much drier and more arid, there are some locations where the precipitation is less than 4 inches per year. So this Oregon State data is mostly usable just for like figures. But you can, this is like 30 years of data that makes this figure up. They also have like year to date, and so you can see, for instance, like this month how much precipitation there's been. So since February 1st, here in West Virginia, if we zoom in a little bit, looks like we in Huntington are in that green zone, which is 2 to 2.4. And so that's since the 1st of February. So, that was less than 3 inches. And remember, we were saying that in certain hurricane-type storms, you can see more than 20. All right, so PRISM is just for visualizing the data. From an engineering standpoint, one that we'll use a lot is the Precipitation Frequency Data Server. And I did show this on that brief video from Friday, so I won't spend too much time going over it. But if you click on the map, and then you can click and drag your cursor to whatever location you're interested in. And you can zoom in if you want to be really precise about it. If we wanted to find out in Hurricane, what's the precipitation like just south of the freeway, then the data that by default it's giving you is the depth. And you can tell from the units there in inches. And so you could find the 10-year storm, 60-minute duration, and it would be 1.87. And even if it didn't have the units in here, you could tell whether it's depth or intensity, because if it's depth, with increasing duration, the amount goes up. Whereas intensity, if you increase the duration, then the amounts go down. So look at how, it's going, for example, 0.556, 0.858. So the amounts are increasing when it's depth, but if we switched over from depth to intensity, the most intense storms are those that have the shortest duration. And so here, the 10-year 5-minute storm is 6.67 inches per hour. But then as the storm gets longer, the average duration, the average intensity during that period is going down. So one of the homework assignments, I ask you to make an IDF table using this data. And to do that, I think you'll need to submit the data, download it as a CSV, and then we'll save it as an Excel file. Let me save this just in a temporary folder. I think maybe some of you have already, in the past, done log graphs before, but in case you haven't, I wanted to show you how you can make a logarithmic scale. All right, IDF table. I really need to set that up automatically to go into silent mode here. Sorry for that. All right, so we've got this intensity, duration, frequency data, and if we wanted to make a figure where we're going to try and make it look mimicked to this one, where we have log scale with duration, and I don't recall what, okay, this is intensity, so we're going to have log scale with intensity on the vertical axis as well. So let me just insert and do a scatter plot, and I'm going to have it not include the data points, just scatter with smooth lines, and you should do the same on the assignment. And select the data, we'll add one, call it the 5-year. The x-axis is going to be the time. Oh, I already need to change this because this needs to have the time in minutes. And so 5, 10, it's got that text there, and it wouldn't be able to graph it with the text. 120, 3 hours, 180, 6 hours, 6 times 60, I guess that's 3. All right, so this is the time in minutes. All right. Need to add some data here. All right, so x-axis is going to be the time. So that's 5 minutes through a day. The y-axis would be the intensity. And then I won't do the other series quite. Well, let me just add one more. I'll add also the 10-year. And the time is just going to be the same duration. The intensity is going to be this 10-year amount. Okay. Now, it's just a simple right-click on the horizontal axis, format the axis, and then logarithmic scale. Once you click that, now we're logarithmic. And let me add the axis titles. So this is duration in minutes, and then this is going to be the intensity. Inches per hour. And same thing, right click, format axis, and logarithmic scale. All right, so we could also turn on the legend, and then that would make it easier to differentiate between the 5, 10, and I think in your assignment I asked you to do, is it through the 100-year storm? Has anybody started on that one?
Yeah, I think it's the 5, 10, 25, 50, and 100.
All right. So 5 through the 100-year storm, just to get some experience making your own IDF tables. All right, and then you'll do the same thing with the depth. So you'll switch over to depth, download this, but then the difference will be once you have the depth data is you're not making it a logarithmic scale for the vertical axis. So the horizontal axis is still logarithmic, but the vertical axis isn't. All right, so that is the precipitation frequency data server. Now, this last one is maybe the most tricky. Let's take a look and see if we can download some actual rain gauge data from NOAA. All of this is statistical extrapolation, and I mean it's all based on measurements of rainfall, but there's no rain gauge in Hurricane that has been around for 1,000 years. Obviously, right? There's no rain gauge in Hurricane that's been around for 100 years. I mean, maybe there's something there that's got 10 years of data, but what they have to do is just kind of take the data that they've got in Charleston and the data they've got in Huntington and kind of interpolate between it. There are some ways, some of the methods that they use for interpolation we'll talk about towards the end of this lecture, but if you want to actually find out the precipitation at a certain location, you can go to NOAA and find a measured rather than a statistically extrapolated precipitation data set. And so what you should do is go to the Data Tools tab on Climate Data Online. If you click on Data Tools, and we're going to find a station. All right, and so let's select a location like Denver. No, I don't want to do Denver. Las Vegas. Oh, that's not interesting either because they don't have very much rainfall in Las Vegas. Like a deer in the headlights. Let's do Detroit. All right, Detroit. So I've selected Detroit, and I want the daily summary. And you have to select a date range. Before it'll show the locations, you have to tell it what range of dates you're interested in. And we want to have as much data as possible. So I'm just going to say I'm interested in 1910 through the present. You have to click on a date, and now that it's in blue, and you say apply, now we've got some weather stations here. And what we really want is just the precipitation data. So, depending on which categories you have clicked, that may affect which data stations come up. So if we click on these, then that's going to bring up a little pop-up that will tell you how much data they've got at that particular location. So I've just clicked on this one, and it tells me that that is, let me pan a little bit here, Dearborn Station number 2. It's got data from 2005 to 2022. So that's only 17 years of data. So that wouldn't be enough to find out like the 25-year storm. And it's only got 95% coverage within that period. So it means that there are a few days that they missed. So that wouldn't be a good one if we were trying to find out what's the 50-year storm. There's not 50 years worth of data there. So we'll just click around here. I'm not sure in Detroit where the airport is. Oh, Detroit City Airport. That's not the main Detroit airport that you fly into, but they do have data here from 1948 through 2022. So that's nearly 75 years worth of data. So that's good enough. I'm going to click Add to Cart. And then over here, you go through this process of checking out. And by default, they want to give you a PDF. But that's not what we need. We need the CSV file, because the CSV file we can open up in Excel. And we want all of the data, so through 48 through the present. So by default, we had earlier told it that we were interested in 1910 through the present, so it carried that through. It's going to give us all the data that they've got at that station. So here's what's in our cart. Now we have to give it our email address after we tell it just to give us the precipitation. You could put all this other stuff in. Like sometimes if you want to be able to distinguish rain from snow, it would be useful to add the temperature categories in. But in our case, we don't need to necessarily distinguish between the rain and the snow if we're just looking for the maximum storms. So I'm just going to have the station name and the precipitation in there, and give my email address. And the longer the data set, the longer it takes for them to email you and let you know it's ready. And then the other factor is how many other people are also requesting data. I've had situations where students submitted their request for data and then they didn't hear back for 2 days. And then there's been other times when I submitted a request and I got it satisfied almost immediately. Like if we click now, check order status, processing. So it's not ready yet. If you have trouble and you're not able to replicate that process that I just went through, there is some data on MyMU in Blackboard. So let me show you. I think I've uploaded the Columbus data set to Blackboard. And we'll open that up just to familiarize ourselves a bit with what the data looks like once you get it. Wrong class. Okay, I think it's maybe in the assignments folder. There it is, Columbus Airport precipitation data. Now, I would prefer that you get data other than just downloading it from Blackboard. I'd prefer that you get the data this way. Let's See if it's still processing. It might be ready. It's complete. All right. So rather than using that Columbus data, I'm going to get the stuff from Detroit. So let me download that, open it, and let's take a look. Okay, so it starts off with the station identification, the name of the station, the date. And remember that these are daily precipitation totals. And the amounts that are listed here, they change the units from time to time, but it's, I think on the handout,
I think you can choose to get them in standard units or...
here's how we can find out which it is if we sort from largest to smallest, and we need to do this for the analysis anyway. So sort from largest to smallest. So these are inches. You know, if we're looking at the amount of precipitation that they've had since 1948 to now, so this is in a 24-hour period, the largest storm that's been observed during that time is 4.07 inches. Now, what could we do with that data? There's a procedure that you can follow to determine your own IDF curve with data that you get from an observed rainfall station. And this formula is in our book, and you can calculate the return period by the total number of years of data divided by the rank of a particular data point. And so, for example, how many years of data do we have? The way that we can do that is let's count how many observations we have, because each one of these observations is a day, right? So let me just count. Okay, so equals count. I think all we have to do is select this entire range, and if you want to go to the bottom of a list immediately, kind of the shortcut keystroke for that is you start at the top, so click at the top and then Shift, Control, and the down arrow. And by doing Shift, Control, and the down arrow, it goes to the very bottom of the list without having to scroll and then just like wait. Because like this has 26,000 rows, and if you're just scrolling to the bottom, it would be like several minutes of waiting. So that keystroke is kind of a nice shortcut. So and we'll close this. So how many, there's this many days. So how many years is that? This divided by 365.25 days per year. So there's 72.5 years of data. So this represents the largest storm that was observed at that airport in 72.5 years of data. And so that is like the top ranked storm. So M is 1 for that. N, the number of years of data, is 72.5. And so T, the return period of that storm, N plus 1. So let's have a return period. This is our top ranked storm. This plus 1 divided by 1. So 73.5 is the return period. This is our second ranked storm. So rank. First rank, second rank. So then this formula, it is this, anchoring it, plus 1 divided by the rank. Okay, so the 36.7 year storm is 3.65 inches. And so we could do that process all the way down through. And we only have 24-hour durations at that location. And so we wouldn't do the same process for like the 5-year storm, the 10-year storm. but you could. This formula holds true regardless of the duration of the storm. It's just how you're calculating the return period. And we had depths here, and if you wanted to know the intensities, remember this is 4 inches in a 24-hour period, and so then the average intensity would be just this divided by 24 hours, and that would give you the 24-hour storm intensity. So just as an illustration, if we had this sorted data where we had the top ranked storm at the top of the list and sorted in descending order, you can see that we've got, if this was from 32 years worth of data, then it would be 32 plus 1 divided by 1 to get the 33-year storm would be 31.5 millimeters. The 16.5-year storm would be 30.2. But we want to know the 25-year storm. That's kind of the common increment would be to report the storm amount for 5, 10, 25, and so on. And so we would have to interpolate in between to report what is the 25-year storm. And so, of course, linear interpolation, you would find the difference in the amount between these two data points. And so the difference between 31.5 and 30.2, so that's 1.3 millimeters of storm depth between these 2 points. And then the difference in time is 16.5 years, and so then you find the slope of the data point. And so this linear interpolation would allow you to take the precipitation amount at the 16.5 year storm, and you know it's going to be more than that. It's somewhere between 30.2 and 31.5, and so it's the 30.2 plus the 8.5 years worth multiplied by the slope of the line, and that linear interpolation would then allow you to report what's the depth associated with the 25-year storm. Now, don't be shocked if a single point is different than what you'd get from the precipitation frequency data server, because measured precipitation at a point can vary a lot compared to the average over an area. And this is the first kind of illustration of that. I had a rain gauge operating in Ona at the same time that the rain gauge was reporting depths of precipitation at the Huntington Airport. And so, a spacing of about 20 miles in distance between the Huntington Airport and Ona. And over the course of several months, the precipitation deviated by, more than 2 inches between Ona and Huntington Airport. And so precipitation can vary a lot from point to point, and some of the reasons for that is depending on where you put a rain gauge, if it's too close to the ground, then there can be splashback from the rainfall hitting the ground and then splashing up into the gauge itself. Now, of course, at a professionally run installation like an airport, they're not going to have any of these variables affecting the precipitation amounts that they report. It just has to do more with, clouds forming over a certain area that same intensity of clouds aren't in the other location at the same time. But some of the things that when you are placing rain gauges in the field that you have to be aware of is if it's too close to buildings or vegetation, that there can be interception of the rainfall. And those obstructions could reduce the amount of observed rain that actually hits the gauge. The low intensity precipitation is a problem because some gauges aren't very sensitive to that low intensity amount if there is a lot of evaporation in between the storm events. So if it was sprinkling early in the morning, then the rest of the day was sunny and clear, and it's one of those manual rain gauges that are observed once a day just by the increase in depth, then there could be evaporation out of the rain gauge that removed all the low intensity precipitation. Now, when you have point values of rainfall amount for a certain storm, and you wanted to find out what's the average within your watershed, the simplest thing that you could do is an arithmetic mean. And that is just simply if you look at all of the rain gauges in the area, in the vicinity of this watershed, they just added them all up and divided by the number of gauges. Now, it's debatable about whether that's a meaningful approach because, for example, this Crystal City rain gauge is outside of the watershed. And so maybe you wouldn't want to give that as much weight as a rain gauge that's actually inside of the watershed. So there's, in order of increasing complexity, different approaches that are taken to try and figure out what should you assume as the average rainfall depth in an area of interest when you've got point data, trying to turn point data into the average over the entire area. So you can see here, if you did this just arithmetic mean, then the average rainfall depth would be 3.26 inches. A more sophisticated approach is the Theissen method. And the advantage of this is it takes into account the distance between gauges and it assigns a depth to the proximity around that rain gauge. So what they're doing in the Theissen method is they're saying, if we take Hangtree and Crystal City, the midpoint between them, you would do a line that is perpendicular to the line that connects them. And so this is a boundary. And anything that's on the underside of that line is going to be assigned the 2.68 inches, and anything that's above that line is influenced by the depth that's observed at Crystal City. And so you do the same thing with Hangtree and Upper Falls. All of the surrounding rain gauges, you put in a barrier, and then you assign the precipitation depth to the applicable area that's enclosed by those barriers between, the borders between gauges. And so this is the Hangtree zone, and you'd find out what's the depth and the contributing area of just that section. And this is a weighted average. Instead of a simple average, like this was, where each of the gauges is given equal depth, this Theissen method has the advantage of assigning a weighting factor that takes into account the proximity of gauges. And so the different areas are multiplied by their depths. And so according to this approach, you'll see that it's a significant different average. The other one said 3.26, but that was undercounting the effect of this heavy 9.1 inches of rain that was measured at the Wyatt station. So now, when you're not undercounting that precipitation amount, then you'd get a higher average, 4.63 inches. So Theissen is an improvement over an arithmetic mean, but we can do even better than Theissen because it's kind of crude breakpoints. If you're saying there's this zone, Upper Falls, that's getting 6.9 inches, and then just right over the border, they're only getting 1.73 inches in the Lynch zone. So that's obviously an oversimplification to have a binary, just a huge step down in the precipitation depth between the two areas. And so the next kind of step up in sophistication, the Isohyetal method, says, well, let's try and extrapolate between these point gauges zones of influence. And it's hard to do this by hand. There are computers that can do it pretty effectively, but each one of these lines represents, it's kind of like a contour line that a rainfall depth is assigned to. And so instead of having it just go straight from 2.68 to 6.9, they're saying, let's do a linear interpolation between those. And so we'll say, here's 6.9, here's 6 inches, 5 inches, 4 inches, 3 inches, and then 2 inches. This is, we don't quite get to 2, but what we're doing is kind of marking linear interpolation between them. And so the Isohyetal method, you can see that these curves are kind of more gradually having the transition of rainfall depth instead of just having a strict barrier where it's going from super high rain to super low. And so again, you would do that in multiple directions. You'd do it between gauges to try and get a feel for where the curvature of the rainfall depths change in each direction. And then you're multiplying the areas enclosed by these contour lines by the depth. And so again, this is more sophisticated than the Theissen method was, but it's going to take more computational time, or a computer would have to do it to be able to get accurate contour lines. Those are just some of the ways that we can take point data and extrapolate it over an area. So there's two important phrases that you need to understand what it means, and temporal distribution is one of them, spatial distribution is the other. And so temporal distribution is a phrase that you could use with this table. Temporal distribution is just saying over a period of time, when is the intensity? How does the amount vary over time? So temporal distribution and spatial distribution is just how does something vary through space? So here's the map of the United States that's showing the arid regions out west. Here's that same map of Hawaii that we've seen before that is showing the effects of orographic lifting along the mountain range on the windward side of the island. Now here's another look at variation on a longer time basis rather than just 24-hour temporal distribution. This is looking at seasonal variations, and it's interesting to notice that there are some places that have their peak rainfall in the summer, and there's other places that have their peak rainfall in the wintertime. So compare Seattle, where they have the lowest rainfall in June, July, and their highest rainfall looks like January and December. But then contrast that to Kansas City, where the highest rainfall amount is during the summertime. And you can start to see why we have different zones in the United States, and it's the different storm causes, the convective lifting in the Midwest that causes most of the highest storm months to be in the summertime when there's more heat to drive that moisture up through the atmosphere, and other places where it's relatively flat and because it's more coastally influenced rather than the lifting due to convection. It's kind of interesting to look at the average number of days with thunderstorms. They're really rare in the western coastal areas where they only have like 5 days of thunderstorms in a year compared to, here in the Midwest, 50, and on the coasts, even more than that. If you want to be able to predict the maximum precipitation that could be observed at a location, then we go beyond intensity, duration, frequency curves, and there's this estimation called PMP, the probable maximum precipitation. And this is looking over everywhere on Earth what is the biggest storm that has ever been observed for a certain storm duration. And it's interesting how it kind of, if you put it on a log-log scale, it follows a line. You can see the formula for that line. This is their attempt to best fit it. Either if you're looking in terms of millimeters, in terms of inches, there's an empirical equation there. But just as a look, in a 24-hour storm, the biggest rainfall amount that's ever been observed, if you go over here, it looks like nearly 40 inches in a single day. So, we live in a relatively wet region here in West Virginia, and we get 40 inches in a year. And what this is saying is that there was a storm one time in Reunion, that is a volcanic island in the Indian Ocean, and it actually holds several of the world records for highest precipitation that was observed. But this probable maximum precipitation is what you could use to really understand the worst case scenario if you want to really stress test a design and find out how is it going to bear up under the most unlikely storm events. This is the most that's ever been measured anywhere. And it's interesting to see that here is a West Virginia location on this kind of world record list. It was a storm that lasted 2 hours. So Rockport, West Virginia has the world record for the most precipitation observed in 2 hours, and it looks like it was about maybe 13 inches of precipitation in 2 hours. Anybody know where Rockport is? I've never heard of it. Where is it?
It's like 20 or 30 minutes below Parkersburg.
Parkersburg?
Yeah, below 77. Or on 77.
It would be interesting to know when that was and what effect it had on Rockport. So they can, with that kind of data, the probable maximum precipitation and just looking at these world record events all across the globe, they further break it down into what is the area over which you expect the precipitation to fall. And the thinking here is that a storm that's localized in a small area is likely to be of a much larger intensity than a storm that's acting over a really large area. So the way to understand this table is that if you have a watershed that is 1,000 square miles in area, then the most precipitation you'd expect within that 1,000, the average over that 1,000 square miles would be 30 inches for the maximum probable precipitation. But now, if you're talking about a 100 mile watershed, then the amount would be higher, 35.2 inches of precipitation, because just the unlikeliness of having a storm covering a really wide area and a really tall column of storm depths, the smaller the area, the higher the intensity. And then, you know, a storm event that's covering 100,000 square miles isn't likely to be as large, simply because there may be pockets of high intensity here or there, but this amount that's listed here is the average over the entire area. So if you have a dam that you're analyzing and you know the contributing area that feeds water into that dam, you'd find out what area is that dam receiving flow from, and then you could use this maximum, the probable maximum precipitation to find the precipitation amount that you'd have to check on. This tells kind of the same story. It's oh, I'm sorry, I've kept you much too late. 12:55. I need to do a better job. So I owe you 5 minutes. I really apologize for keeping you late. We'll leave it there for today.